Okay, so we're gonna do a couple of properties that come from similar triangles and proportional relationships. The first thing we're gonna have here is what is called the side splitter theorem. Okay, so this is a pretty straightforward thing. It says that if I have a triangle and I call this, let's say it's A, B, C, and I draw a line, we'll call it XY, in such a way that this line is parallel to the base, then the following proportion comes out. AX is to XB as AY is to YC. Okay, so let's kind of do a quick little synopsis as to why that is. There's a full proof in your notes. I'm not going to walk through the entire proof, but I'll walk through the logic of it here. If these are parallel, then these two angles have to be congruent because of the corresponding angles postulate, and so do these. Once I have that, I know that triangle AXY has to be similar to triangle ABC by AA similarity. And from that, I can get a proportionality statement. I can say that AX is to AB. Actually, I'm going to be more cautious about how I do this. I'm going to make AB is to AX. There we go. As AC is to AY. Okay, because this is big triangle, small triangle, small triangle. All right. If you look, though, AB is the same as AX plus XB. And AC is the same as AY plus YC. Okay, so let me move up here a little bit. Looking at that, I can break that into AX over AX plus XB over AX is AY over AY plus YC over AY. Anything over itself is 1. Same thing here. And subtract 1 from both sides. I get XB over AX is equal to YC over AY. And then just flip both fractions of the proportion over. So you get AX over XB is the same as AY over YC, which is precisely what I tried to prove. So if you split the sides of a triangle using a parallel line, or a line that's parallel to the base, then it splits the triangle's sides proportionally. Okay, the converse of this is also going to hold. Okay, so the converse of the side splitter theorem says, well, what if I have the triangle and I draw the line? So this is going to be A, B, C, and we'll call that XY. And I draw the line so that the proportion holds, right? So what if XB is to AX as YC is to AY? Well, then can I prove that that line's parallel? Well, you just kind of work it all backwards. Add 1 to both sides, right? So I get this is equal to 1 plus YC over AY, right? Turn the 1 on the left into AX over AX plus XB over AX is AY over AY plus YC over AY. Combine the fractions, I get AX plus XB is equal over AX is equal to AY plus YC over AY. Well, AX plus AB is just XB is just AB over AX. AY plus YC is just AC over AY, which gives me that this side is proportional to its whole. That side is proportional to its whole. A is congruent to itself. So I have triangle AXY is similar to triangle ABC by SAS similarity. If these triangles are similar, then the corresponding angles have to be congruent, which means angle X has to be congruent to angle B. If those angles are congruent, then those lines are parallel, which means that the converse holds. So if I have proportionality, then I get parallel. All right, so we're going to get a corollary of this. Okay, so the corollary basically says I don't actually need the triangle. I just need 3 lines. So that if I have 3 lines that are all parallel, and they cut 2 transversals, so let's call this A, B, C, F, E, D. Well, then what do I get? I know that A, B is to BC as FE is to ED. Okay, so how do I know that? Well, here's the thing. If you take this line and you slide it over to this point, then we know that this and this are proportional to this and this, and these 2 lines are basically the same. You just slid it over to the right. So that means this proportion is going to hold as a direct result of the side splitter theorem. We don't need any additional proof there. All right, so we've got one more theorem, and then we're done for the day. Okay, so in this theorem, we're going to start, I'm going to draw carefully a triangle here. Here we go. I set myself up nice for the proof. I'm going to call this triangle ABC. And what I want to do is I want to draw in this ray such that I get the angle bisector. Okay, so this AM is going to be the angle bisector of angle BAC. The argument is that if that's true, then the following has to hold. AB is going to be to BM, so this and this are proportional to AC over MC. Now that seems almost incredulous, but it is in fact going to be true. So here's how I'm going to do this. I'm going to take out my ruler here a little bit, and I'll show that this is true. I'm going to extend that segment AC a little bit here. So let's get a different color. We're just going to extend that thing out. Okay, and then I'm going to take my ruler and I'm going to turn it again. This time I want to turn it so that I'm going through B and I'm parallel to AM. So let's draw that in. There we go. Okay, so I did that construction, and I can always do that construction. We're going to call this point X. Okay, so if I do that, since I know these are parallel by construction, that angle there and that angle there, they have to be congruent, which means, in fact, all 3 of these angles are congruent. Okay, so if I look at this, I also know that because these 2 are parallel, that angle and that angle must be congruent. So I actually now have 1, 2, 3, 4 congruent angles. The key here is going to be this guy and this guy, because that makes this triangle right here an isosceles triangle. If those two angles are congruent, those two sides have to be congruent. Okay, so let's kind of work out what we got here. If I look at this, I now have a line coming through here that's parallel. So by the side splitter theorem, I believe that I have AC is to AX as MC is to BM. Okay, so AC is to AX as MC is to BM. But I just showed that AX and AB are the same. So AC is to AB, because AX and AB are the same, as MC is to BM. Okay, so if I cross multiply here, alright, so I'm going to put that over here. I'm going to get AC times BM is equal to MC times AB. Okay, so I cross multiplied and I got that. Now, let's divide both sides by MC times BM. If I do that, the two BM's cancel, right? Leaves me with AC over MC. Over here, the two MC's cancel. It leaves me with AB over BM. And if I take a look at that, and I take a look at this, what I'm trying to prove, those two statements, AB over BM is equal to AC over MC, say the same thing. So let's recap that one so that we know what the theorem actually says. Okay, so theorem here, remember, I have a triangle, A, B, C, dropped in the angle bisector to M, and I said that AB is to BM as AC is to MC. That's the statement of the theorem that we just proved. So we get a side splitter theorem, we get a corollary from the side splitter theorem and a converse, and we get this little bit here exactly from the side splitter theorem that deals with the angle bisector. Alright, there's one little last tidbit in the notes there that we want to make aware of. Okay, so this little piece basically says that if I have two triangles and they are similar, and let's say they have a scale factor of 3 to 2, so my scale factor is 3 to 2. Okay, so this means everything on this side I would multiply by 3, everything on this side I'd multiply by 2, and I'd get the correct scale factor. So this means that the ratio of the perimeters is also 3 to 2. The ratio of the areas, however, is going to be squares of that. So it's going to be 9 to 4. So what we're saying here is if the scale factor is A to B, the ratio of the perimeters is also A to B. The ratio of the areas is going to be A squared to B squared. So let's say that I knew that the perimeter of this was, let's say, 9, and that its area was 27, right? So it's going to be 9 units and 27 square units. Then the perimeter of this one, well, let's see, 3 times 3 is 9, so 2 times 3 is going to be 6 units, And the area of this, so let's see, 3 squared is 9. 27 divided by 9 is 3. And 4 times 3 is going to be 12 units squared. So these are kind of quick, handy ways. If you're given the perimeter of 1 and the area of 1 and you have the scale factor and you know that they're similar, you can get the perimeter and area of the other one. Thank you.